Hey guys, in this video I'm going to be going over problems 11 through 15 of the 2017 AMC12B. This is problem number 11 and it reads, call a positive integer monotonous if it is one digit number or its digits when read from left to right form either a strictly increasing or a strictly decreasing sequence. And it asks how many monotonous positive integers are there. There are two different cases to consider when solving this problem. The first case is if all the digits in the integer are strictly increasing, and the second case is if all the digits are strictly decreasing. So for the first case, when all the digits are strictly increasing, which we'll call case 1, we can't have a 0, because if we have a 0, then that would have to be the first digit, which is not valid. So we can only use the digits 1 through 9. And the key realization to solving this problem is that if we have n digits, then there's only one way to form a strictly increasing sequence and one way to form a strictly decreasing sequence. So for example, if we have 5 digits, then there's going to be 9 choose 5 strictly increasing sequences. So by this logic, for the first case, there's going to be 9 choose 1 plus 9 choose 2 up until 9 choose 9 strictly increasing monotonous integers. And there's a formula for this kind of sum, and that's if you have n choose 1 plus n choose 2 up until n choose n, this is 2 to the n minus 1. And so applying this formula, we have this number being equal to 2 to the 9th minus 1, which is 511. For case 2, which is the case that the digits in the monotonous integer are strictly decreasing, we can use the digit 0 because that means 0 is going to be the last digit rather than the first digit, which is going to be valid. So here we can use 10 different digits, which are 0 through 9. And now we can just apply the exact same logic as we did in case 1, except for one thing. With 9 choose 1, we counted the number of strictly increasing one-digit monotonous integers. And that's actually the same thing as the number of strictly decreasing single-digit monotonous integers. So basically, what we can do is just not count 10 choose 1. And conveniently, 10 choose 1 also includes the number 0, which we also have to exclude because we can only look for positive integers. So basically, what happens is that we're only left with the sum 10 choose 2 plus 10 choose 3 up until 10 choose 10. And this is equal to 2 to the 10th minus 1 minus 10 choose 1, which is 10. And this is equal to 10, 13, I think. So the last step is just to add these two, 511 and 1013. And after we do that, we find that we have 1524, which is B. This is problem number 12, and it reads, what is the sum of the roots of z to the 12th equals 64 that have a positive real part? To find these roots, we have to know the formula r times cosine theta plus I sine theta to the nth, to the 1 over n power. So the nth root is equal to r to the 1 over n times cosine of theta plus 2 pi k over n plus I sine of theta plus 2 pi k over n. The next thing we have to do is plug in the values for the problem. So we have r equals 64 and n equals 12. So we have 64 to the 1 over 12 times cosine theta plus 2 pi k over 12 plus I sine theta plus 2 pi k over 12. So actually I forgot to explain that k is going to be 0, 1, 2 up to 11. And for each of these values you plug in, you're going to get a root. So in total, you're going to have 12 roots. And here, theta has to be, well, it doesn't have to be, but we'll set it to 0 because in this case, r is 64, and we have it multiplied by something all to the 1 over 12. So this value, since we're taking 64 to the 1 over 12, this value has to be 1. And one way to do that is to have theta equals 0, which is cosine of 0 plus I sine of 0. Sine of 0 is 0, so and cosine of 0 is 1. So we know that theta is equal to 0. Since theta is 0, we can just cross those out. And the 2 cancels with the 12, so we'll just leave a 6 on the bottom. 64 to the 1 over 12 is the square root of 2. And if we're looking for the positive real part, the real part will always come from the cosine value, since the sine value is going to be multiplied by an I. This leaves, to make it more clear, I'm going to rewrite this as the square root of 2 times cosine of pi k over 6 plus I sine pi k over 6. The positive cosine values will occur in the first and fourth quadrants, since the cosine value is going to be the x-coordinate. And that's going to be when k is 1, when k is 2, when k is 0, when k is 10, and when k is 11. Conveniently, the sine values will cancel because they're kind of mirror images of each other in the y for the y coordinates. So we just have to look at the cosine values. So we have cosine of pi times 1 over 6, which is 30 degrees. And we also have the mirror image of that in cos of 330 degrees. So we can just multiply that by 2. Similarly, we have cosine of 60 degrees, which we have the mirror image of in cosine of, I think, 300 degrees. And we have cosine of 0 degrees. If we add these up, we have cosine of 30 degrees is square root of 3 over 2. I'll make some space real quick. So writing this out, we have 2 times square root of 3 over 2 plus 2 times 1/2 plus 1. And this is going to give us square root of 3 plus 2. However, we have to remember to multiply by the square root of 2, which will give us square root of 6 plus 2 root 2. And that is D. This is problem number 13. It reads, in the figure below, 3 of the 6 discs are to be painted blue, 2 are to be painted red, and 1 is to be painted green. 2 paintings that can be obtained by one another by rotation or reflection of the entire figure are considered the same. How many different paintings are possible? There's 2 cases as to where we can put the 1 green disc. One possibility is if we put it on this disc, because this disc can be rotated to this position, and this position. The second possibility is if we put the green disc here, because it can be rotated to this position and this position. So in the first case, if we put the green here, which is also the same as putting it here or here, then the next thing we have to do is know where to place the reds, because after that, the 3 blue discs will just be the remaining ones. And the reason why I do it in this order is because if I place the blues directly, if I just counted directly how many cases there were to arrange the blue discs, there would be a lot more cases, and it would be a lot easier to make a mistake. To count the number of ways we can arrange the 2 red discs, we can actually use complementary counting. And how we do this is we determine how many ways there are to paint 2 of these discs red, and how many are going to be the same? How many colorings are going to be the same if we rotate them? So there are 5 choose 2 ways, which is 10 ways to actually choose which 2 discs get painted red. And we can count how many there are, how many colorings are considered the same. So if we color these 2, this is the same as coloring these 2. So that's 1. If we have these 2, that's the same as coloring these 2. That's 2. If we have these 2, it's the same as coloring these 2. That's 3. And if we have these 2, it's the same as coloring these 2, which is 4. So basically, we just say 10 minus 4 equals 6 different colorings, or 6 different ways to arrange the 2 red discs. So let's move on to case 2. Case 2 is when the green is here. And I'm going to erase the green that's up here. So how we do this one is kind of in the same way. So again, we have 10 ways to choose the 2 red discs since we have 5 slots available. And then we count how many there are that are the same by rotation. So we have these 2 being a rotation of these 2, these 2 being a rotation of these 2, these 2 being a rotation of these 2, and then we have a little more subtle, these 2 being a rotation of these 2. So again, there are 4 arrangements that are equivalent by rotation or reflection. So again, we have 10 minus 4 equals 6 possibilities. And adding these 2 cases up, we have 12, which is D. So this next problem is number 14. It's a geometry problem, and it asks, an ice cream novelty item consists of a cup in the shape of a 4-inch tall frustrum of a right circular cone with a 2-inch diameter base at the bottom and a 4-inch diameter base at the top, packed solid with ice cream, together with a solid cone of ice cream of height 4 inches, whose base at the bottom is the top base of the frustrum. What is the total volume of the ice cream in cubic inches? So the first thing we want to do is to draw the diagram. So we have the 4-inch tall frustrum with a 2-inch diameter base at the bottom and a 4-inch diameter base at the top. So we have this at the bottom and something like this at the top. And its proportions were a little bit off, so I'm going to redraw it. Should look something like this. And then you have the 4-inch tall ice cream. And this is 2 inches. This is 4 inches. This is 4 inches tall. And this is also 4 inches tall. So to compute the volume of the entire thing, we have to first compute the volume of the cone and then the volume of the frustrum. So for the cone, the formula is 1/3 pi r squared h. And just plugging this in, we have r is 2 because the diameter is 4. So we have 4/3 pi times 4, which is 16 over 3 pi. If we look at the frustrum, we notice that it's basically a larger cone with its top cut off. So if we just flip it over to make it look simpler, it's basically a large cone with diameter 4 with the top cut off. Right. This is 2, and by similar triangles, if this is 4, then this top part is also 4. So what we want to do is calculate the volume of the entire thing and subtracting the volume of the smaller cone. So basically we just have 1/3 parentheses pi, this is 2. 2 squared h is going to be pi times 4 times 8 minus pi r squared, r is 1, times the height, which is 4. If we do this, we get, this is 32 pi minus 4 pi, which is 28 pi. So this is 28 pi over 3. And all that's left to do is just add these two, and we get 44 over 3 pi, which is e. This is question number 15. It's another geometry problem, and it reads, let ABC be an equilateral triangle. Extend side AB beyond B to point B prime so that B prime equals 3 times AB. Similarly, extend side BC beyond C to a point C such C prime so that C prime equals 3 times BC. And extend side CA beyond A to a point A prime so that A prime equals 3 times CA. What is the ratio of the area of A prime, B prime, C prime to the area of ABC? So again, we have to draw a diagram. Let's call this ABC. We have to extend AB beyond B. Get B prime. Extend BC beyond C. Get C prime. And CA beyond A to get A prime. And we have to draw the entire triangle. In these geometry problems, where they ask for the ratio, you can set arbitrary values in order to make the problem more convenient. So for example, if we make ABC have side length 1, we know that A prime is 3, C prime is 3, and B prime is also 3. And this makes the problem a lot more convenient. So that's it for this video. If you enjoyed, please leave a like and subscribe. I'll post a new video every Friday. Thanks for watching, and I'll see you in the next one.